The recording has started, Professor, so I wish you good luck, all right?
Okay, thank you very much. So, well, Professor Baruch, thank you once again for your time on doing this grading of this very exciting exercise for our speaking skills. So this is
My
the
pleasure.
title of my topic presentation. It's named N-heterocyclic ligands, and it sits in chemical bond forming reactions. This is actually a topic from my second unit of the organic synthesis class, which I lectured to students of the seventh semester of the Bachelor in Chemistry here at the university. So
Got
this
it.
is a high-level class of organic chemistry. So I hope I don't confuse you too much because some terms are not too basic, but I'll try to do my best so I can explain myself well.
Perfect.
So
Thank you so much.
uh, let me begin with the definition of what is an NHC ligand. See, for some, okay. Yeah. So these ligands are actually constructed from a species called stable carbene. These carbene are actually defined as molecules which contain carbon atoms with two different substituents, and that also have a very special feature of having an electron pair in the carbon atom. So in chemistry, in basic chemistry, we define a stable molecule as a molecule that contains at least 8 electrons surrounding each atom on the molecule. So because the carbenes only have 6 electrons, these molecules are considered as highly unstable. So there are two different types of stable carbenes, which depends on the location of the electron pairs. The first one is defined as singlet carbene, in which the two electrons are located into the very same p orbital. I'm not sure if you had some chemistry class before, Professor, but I hope I can do well so I can give you an overall idea of what this means.
So far, so good. Perfect.
Okay, cool. So the second type of carbenes is called triplet carbene. So in this case, the electron pair is located in two different orbitals. So because of this situation, the most stable carbene is named the singlet carbene because the electron pair follows a rule which is named the Lewis rule, in which two electrons must be located in the very same position on an orbital, okay? So actually most of the literature reports that now we have available regard precisely from the use of singlet carbenes in metal chemistry. So because of the high instability of these complexes, of these carbenes, they were believed only to be transient structures in chemical bond forming processes. But fortunately, in 1988, Professor Guy Bertrand, which I must say, I'm very proud because I was one of his students during my
Wow.
PhD, he was able to isolate the first free stable carbene. This carbene was stabilized by a phosphorus and a silicon atom, but unfortunately, because of the high flexibility around the carbon center, these ligands were not able to coordinate to metal centers. So 3 years later, Professor Arduengo was able to insert the carbene center into a more rigid structure. So in this case, the angle between the nitrogen, the carbon and nitrogen was available for transition metals to coordinate this center. I must emphasize that if Professor Arduengo had not isolated this type of molecules, we wouldn't have explored the possibility as ligands for transition metal chemistry. So this was actually a great breakthrough in organic chemistry.
And a quick question, sorry. Do you
Yeah,
have the opportunity to meet Professor Arduengo as well?
yeah. So actually, Professor Bertrand and Professor Arduengo, uh, a lot of people working on chemistry is mentioning that they may probably be able to earn the Nobel Prize because of the discovery. Because this was
Wow.
actually a high breakthrough in organic synthesis, because transition metals are usually used for catalytic processes, which allows the formation of new carbon-carbon bonds, which is of course a paramount topic in organic chemistry. So yeah, I had the fortune to meet them in chemistry congresses taking place on the United States. So yeah, it was this was a very exciting time for me while I was a PhD student. And also, I must say that I had the fortune to go to Germany and had conversation with 30 Nobel Prizes in chemistry. So I had the chance to talk to them. So it was really an exciting time in
Of course.
2013 when I had the chance to do that. So, well,
Amazing.
anyways, yeah,
Thank you for
thank you.
sharing, Professor
No,
Daniel.
thank you for your question. So after these carbines are isolated and they are used for coordinated transition metals, then the question that arises is how do we construct these molecules, right? So in organic chemistry, there is a very specific reaction that is used for generating these molecules, which relies in the reaction of an internal alkyne in which two carbon atoms possess a triple bond. They proceed to do a cycloaddition with a molecule called organic azide, which contains three neighboring nitrogen atoms. So after the catalysis with a copper 1 species, then we can generate these 5-membered rings, which I'll call 1, 2, 3 triazoles. This triazole has the feature of containing a CH bond that we will see after can be removed in order to proceed to the formation of the free carbines. This molecule, which was developed in 2001 in a process called click chemistry, then needs after to form a new nitrogen methyl bond by the reaction with a reagent called methyl iodide. So in this case, we are changing the coordination number of this nitrogen from 3 bonds to 4 bonds. And so this nitrogen becomes positive. This molecule then is a cation, which enhances the acidity of this CH bond. So this is important because we can remove more easily this CH bond compared to the neutral form. So this is actually an NHC carbene precursor. So
sorry, a question. I mean, just you mentioned something that catch my attention just out of curiosity. You mentioned that it enhances only the acidity levels of that part of
the
uh,
molecule,
saline or salt solution.
the
Does
salt.
it only enhance that attribute or some others?
No, it's only this one because in a acid-base chemistry, we used to work with proton atoms only, not carbons, not nitrogen. So this is only related to the CH bonds. So the whole molecule has a positive charge that keep me changing from the nitrogen atoms, but the position that is most affected is the CH position over here. And so this is good because we can take advantage of the change on the values of the acidity in order to generate the molecules now referred as free carbines. So please let me explain this a little bit more. For instance, once we have this molecule with a positive charge, then we can make it a reaction with a base. And so we will detach this hydrogen atom from this position and then generate the free carbene. This free carbene, having the electron pair available for coordination, then in a further step can be reacted with a metal atom in order to generate the transition metal complex. In case that the free carbene is not available for reactivity, then we must follow a second methodology in which the cationic species are reacted in a single step with a base in presence of the metal. So the carbene is not isolated, but is generated in situ the reaction. So because of his very high reactivity in presence of the metal, we can obtain then the coordination complexes in just a single step. So this is actually very nice because a lot of free carbene species are not stable. So in the lab of Professor Bertrand, when I was working as a student, we could develop this type of methodology. And so now this methodology is being used worldwide to produce this type of complexes. So the triazolium salt then is very important as precursor for generating either the free carbene or method B, in which we can generate the transition metal complex in just a single step. Okay. So with this, Professor Baruch, please let me ask you a quick question. Is it understandable why free carbenes are recognized as highly unstable species. Do you remember which was the electronic feature that was mentioned in order to consider them as highly stable species, unstable species?
I do not remember quite
Okay.
clearly. Nevertheless, just to be quite honest, nevertheless, I do happen to see over here that if we happen to have two different methodologies to go into the metal, I even got that one into a blurry kind of state. But the final kind of stage over here, I suspect that, yeah, we are dealing with a lot of instability
Yeah.
into the matter, right?
So yeah, just to clarify that point. So carbines are not very stable because they only have 6 valence electrons. Remember that
Right.
for a molecule to be stable, they must have surrounding at least 8 electrons. Okay, so this is the case. Only 6 electrons are not stable for generating molecules with a high level of stability, right?
We need at least 8 of them.
Okay, so that's the gold rule in chemistry, the octet rule, which is called. So well, don't worry. Even from students from the 7th semester, they even had trouble with that. So you are doing quite well, eh?
The golden rule, right?
I now understand why are you so great, professor. Um, so let me continue with a demonstration of some catalytic application of these NHC ligands. So after their
Mhm.
discovery, a lot of research has been targeting the generation of new complexes using these cationic precursors in presence of a base and with different metal sources. So as you can observe from the slide, you can generate complexes with palladium, with rhodium, with gold, which are very useful because each metal has a different application in organic synthesis. Also, you can observe that the yields of conversion, which means how much of the starting material is transformed into the products, is very high. The yields range between 70 and 93%, which is actually very high. And this is also very valuable because metals are very expensive. So the higher the conversion you have, well, it's the better benefit for the organic synthesis. All right.
Of course.
So, well, with these simple structures, then research has been also devoted to generate more complex molecules. As you can observe also in this slide, now there are available structures that have a single ligand containing 2 carbonic centers and even 3 carbonic centers. So this type of design of the ligands was actually aiming to compare what will happen if I have a molecule with only one metal center and how will this compare with a ligand that has more than 2 metals? Is really the
Mhm.
number of metals important for the catalytic transformations? So in this case, for the catalytic application, let me show you this scheme in which we can observe that these starting materials containing a functional group called ketone and having a carbon atom in a neighboring position in the presence of a base and in the presence of the catalyst can form a new carbon-carbon bond between this species and a phenyl group of a bromophenyl substituent, right? So this is
Well,
the general scheme. The complexity of the formation of the new bonds, as you can observe, is very high, containing simple phenyl groups, but also phenyl groups with different substituents. So the reaction was very good because it's allowing us to generate new carbon bonds. And this is the graphic that demonstrates the comparison between the different metals that have been studied for this purpose. For instance, L1, which indicates that we only have one palladium center or one palladium metal, can perform the synthesis of this first example only in 65% of yield.
mhm.
The ligand that has 2 metals increases the yield over 70, but the ligand with 3 metals, which is this one, can go almost up to
Of
quantitative
the point.
conversions, right? And this is actually the very same behavior that we have in the several derivatives that I have shown you before. You can observe that the ligand with the 3 metals is the one that